We're gonna follow on after this initial discussion with Dr. Daniel Renner. Dr. Renner is the currently representative at IOEEE Photonics Society for the Industry and Engagement Committee. But before getting there, let's say a few words. Dr. Renner is from Chile. We're in Patagonia, actually. And he received his engineering degree from University of Chile, and then moved on to Cambridge, UK, to pursue his PhD in Photonics. Later on, he delved into the whole photonics industry initiative, manufacturing, commercialization of photonic devices, and various other aspects of the photonics industry. And over the past 30 years, he actually involved in the growth of 4 photonic startups. I think they're very in the spirit of this workshop. And a few of them is Orkel Corporation, Agility Communications, Ayers Photonics, and Freedom Photonics. So it's a great pleasure to have you here, Daniel. Looking forward to your insights.
Thank you very much for the introduction, and it's great to be here. And what I want to do is to share what life is at a photonics startup from my own very personal experience. We've had earlier this morning 3 very interesting talks, also looking at it from a very personal vantage point, and I'll do the same from my perspective. As you can see from my face, I've been around for a while, so it'll be a very long talk. Don't worry. I'll try to speak all within 30 minutes. And, but it is a very personal experience from my professional trajectory, what I have done through these years. But mainly out of what I've done, what are the lessons learned? What can we say about this experience teaching us in terms of creating business plans, budgeting, things that were already mentioned in the previous talks, and you'll see a certain sense of commonality. You'll hear some of these things again. So if you hear it from more than one person, I guess it must be true. And also ending up with some thoughts on the creation of a successful photonics startup ecosystem. And that will be sort of towards the end. So let's start from the beginning. So this is me. Oops, what happened there? There. So this is me, age 4 or so. And that's where the photograph was taken, which is where I'm from. So not that far, not that close either, but not that far. Not far in an intellectual and emotional sense. I'm from South America as well, and I understand, I think, I hope, some of the issues that you face as you try to get your career path, your work, your life going forward. And this is my trajectory. I decided after studying for my first degree in Chile to do a PhD that, as was mentioned, I did in England. Then I worked for a brief amount of time in England, and then for most of my life, actually, I've been in the United States, in North America, first in Dallas, Texas, and then in California. So I think I'm in a relatively unique position where I think I can understand South America, Europe, and North America. And my hope, and it is also the hope of the IEEE Photonics Society, that through events like this and through sharing my experience, I can help, and the society, the Photonics Society, can help develop the photonics ecosystem, the photonics world in Brazil and in Latin America. So this shows exactly where I've been from a photonics perspective. As I said, I got my first degree at the University of Chile. And then from there, I went to the University of Cambridge in England, where I got my PhD. That was way back when. Photonics was right at the beginning. So almost any kind of stupid thing you did was worthwhile. It didn't matter. It was crazy, but it was worthwhile. Then after that, I worked in two large companies. First for ITT in England, and then I went to the United States. I worked for Rockwell, which both of these were actually. They don't exist any longer, these large companies. Not my fault. I had nothing to do with their disappearance, but basically they disintegrated. But anyway, they were thriving at that time, and Rockwell. And then from then on, I went through sequentially a series of startups. Ortel was the first one, then Agility, Arios, Freedom. And we sold Freedom Photonics last year to Luminar, which is a company in the automotive LiDAR field. That actually CB mentioned. And I stayed on for a year after Freedom was sold. And at the beginning of this year, I decided to change my direction. I decided not to work for a single company any longer. I left Freedom Luminar and I formed this company called Atacama. For those of you who know geography, it's a desert in the north of Chile. So it's an obvious choice for me. And Atacama is a consulting company. So I split my time between consulting for various other small companies and volunteer work, as Natalia mentioned earlier, for the IEEE, trying to help where I can. So if we go into some detail, I started at, as I say, ITT, Standard Telecommunication Laboratories in England, which, by the way, is where Charles Keo started doing experiments on optical fiber in the 60s. This was way before I joined STL. I'm old, but not that old. So he actually, you probably know, if you're involved in fiber optics, he many years later got actually the Nobel Prize in physics for his work in fiber optics. So actually STL is where fiber optics started. And I was lucky enough some years later to be accepted there and work in photonics. I was very lucky actually that my first job actually was joining a team that was developing lasers, diode lasers, for the first underwater fiber optic cable system in the world, SAT-8, which was started operation in 1988. So we were developing the diode lasers that would optically power the transatlantic cable. This was the first one to go under, SAT-8 in 1988. And it was designed to operate for 25 years. And in fact, it operated until 2010 for 22 years. And the reason that it stopped operating, actually was recovered from the bottom of the ocean. It's not that it failed technically, it was still operating very well. It was not, again, I was not at fault. The diode lasers worked very well. But the reason that it was taken out of the ocean 22 years later is that the total capacity of SAT-8, the first fiber optic underwater system in the world, was 44 megabit per second. And you can think of now at home, you're getting more bandwidth than that. And that was huge at the time for the whole of transatlantic communications. That was revolutionary compared to coax cable, which was being used before. So this is a piece of the recovered SAT-8 cable. And actually that picture there is me. This is a display at the Science Museum in London. And that's me looking at this piece at the Science Museum in London. I'm trying to figure out, what does it mean that a piece of something that you participated in, that you contributed to, It's now in a museum. And my answer to this is what it means is that I'm really old. That's all it means. The thing is now a piece of the museum. So that 8 was tested before deployment, which was a good idea. Before laying it out around the Atlantic, part of the cable was laid out around the Canary Islands in 1985. You remember the whole cable was laid out in 1988. The test was done in 1985. And the cable failed. And the reason that it failed is that some sharks bit into it. And there were shark teeth encrusted into the cable that were found when the rod failed, what happened. And they retrieved the cable and they found shark teeth in the cable. To be entirely honest, well, after that, the cable, because it was optical fiber and so not susceptible to EMI, to interference, it was thought, hey, it doesn't need much metal, not much reinforcement. That changed. It's not needed for reinforcing it to isolate it, but it's needed to prevent it to be attacked by sharks or anything. It's an interesting thing because actually I looked for it later, and at least what's publicly known, I don't think that now, as you know, there are fiber optic cables at the bottom of the ocean everywhere. And I don't think there's been ever any other attack of this nature. I don't know what happened there. It was a crazy shark or whatever happened. But in any event, it was good that it was tested early. And being a, being a young practitioner of engineering at the time, I was around 30 years old or thereabouts, I was learning, one of the things I learned, that high-risk, difficult problems should be tested as early as possible, ridiculously early. I found this as a very valuable lesson. Test as soon as you can. And in the case of that 8, a lot of what we were doing in terms of lasers was new. And so we did a lot of early testing. Not only the whole cable was tested early, but a lot of reliability testing on the diode lasers. Stressed them infinitely. Things like laser welding for packaging, which is something that in photonic packaging is used now commonly. We were actually the first group that tried laser welding for photonic packaging. So there were a lot of unknowns, and the best way to transform the unknown into known is, hey, test the heck out of it. So this is the team that developed the digital, the lasers, the diode lasers. So where is Daniel here? Actually, I'm here. So it's just like me, but with brown hair. And it was a relatively large team, about 35 people or so. That's a large team, but it was an important mission, as it were. And we worked very well together. It was again, I was lucky that in my first job, I found a very interesting mission and also a team where the culture was to share, to work together, to be together. We spent a lot of time socially together. So the lesson number 2 is that industrial product development is a team effort. This for me was, in a way, I mean, it's not surprising, but it was a shock. I had finished my PhD, which by definition is a very solitary effort. I don't know what your experience is, but to me, I worked alone, and most PhDs work alone, which is really a bit of a problem in the sense that you're formed to work alone, and then you go into industry, and you're expected to work in a team and to collaborate and to work together with a lot of other people. And you have to, because it is impossible. It really is impossible, of course, to develop a product alone. It's a team effort. It's more like a football team than a golf player, and that's the way industrial development is. And lesson number 3 was you should work with people that you like. We really liked each other in that group. And actually, this happened in the 1980s. And to this day, I'm in touch with the people that I work with there. Beyond being colleagues, we became friends. And with several of them, I'm friendly still today. And that's a lesson that I would recommend highly to you. You spend with people you work with most of your life, actually. So why not to be friends? It's kind of part and package of what's there. So then from STL, I went to Rockwell in Texas. That was a time when fiber optics was now exploding. I was lucky to be in one of the first sort of implementations in TAT8, but then at this time, landline systems were being deployed all over the world. And Rockwell Collins was a division of Rockwell, a larger company that had a long history of radio. Collins Radio had been formed in the 30s and became a dominant force in radio, but obviously with fiber optics, radio was going down the drain. So they saw the writing in the wall, and they actually managed to convert the company into a dominant fiber optic company as well. And my hiring, I mean, they hired a lot of other people. Again, I had a small, tiny contribution like this size, but I was part of being able to make that a success. So again, I was lucky where I fell in that Rockwell was very dynamically pursuing the landline fiber optic system. And actually, we were the first company that offered commercially a system that operated above a gigabit per second. Today, obviously, there are systems that are much faster than that, 10 gigabit, 100 gigabit. But 1 gigabit was a major breakthrough. And this is actually a piece of news where it said that a Rockwell system had been installed, operated at 1.13 gigabit per second. And in this race to be the first commercial company to have a commercial system deployed above the gigabit, we were racing against AT&T Western Electric, which was a dominant company at the time, and many others worldwide, LM Ericsson, et cetera, et cetera. And we knew we were in the race. We knew we wanted to be number one. And we developed this system in just 1 year, which is astoundingly fast. And lesson number 4 then is that a talented and motivated team on a mission can beat the dominant top company. The impossible is possible. We were the underdogs. They were the dominant company, but we were the first out there. So being able, and this is something that CB mentioned a little bit earlier, being able to select a team that is better than you, that is highly talented, and that is motivated is crucial to success. At Rockwell, I had a dual, which seemed to be apparent contradictory role. On the one hand, I was the person that was supposed to develop and manufacture optoelectronic components internally. We had a group that was making diode lasers, photodiodes, and so on for use within Rockwell. And at the same time, I had to evaluate and select external suppliers. So in a way, my competitors. I wanted to make DFB lasers for Rockwell, but I at the same time had to select external potential suppliers and suppliers of DFB lasers. And this sounds contradictory, but in reality, it is not. I really had, from a business perspective, only one role. My role was to be able to provide the best photonic components that the Rockwell Systems group required, and best from a performance and cost basis, whether these were made internally or they came externally. And there was a balance, a very complicated balance of dependence on an external supplier or independence from that supplier, cost, performance, that all came into an equation to determine who would be the supplier into Rockwell. And that was my role. So to be able to perform that role effectively, I had to become more involved with the business side. And for example, the system that I mentioned, the 1.1 gigabit per second system, used photodiodes that were made internally because those were at a cost and performance that was acceptable. But the DFBs were provided by external suppliers initially because our internal DFBs initially were not cost effective enough. Eventually, we replaced the external suppliers with internal. So it is important here, 3 lessons to understand that you are developing products that provide value, that solve problems. If what you're developing is not solving the problem because it's too expensive, for example, then you're not solving anyone's problem. And that is something I had to understand. And lesson number 6 is something that actually Carlos mentioned, and then somebody made a question that this was not entirely clear, but I didn't talk to Carlos, so we kind of written this down totally independently, that it is dangerous to fall in love with the technology and lose sight of the business. And this is something that happened to me, I think happens to every engineer, to every technologist, to every PhD. You love the technology you're working in and you get blinded by everything else. And if you go to industry, which I hope you will, because it's fascinating, industry is about business. So it's a combination of both worlds, the business world and the technology world. And actually it is technology serving a business purpose. So the business purpose has to be there all the time. So you cannot get blinded by your love of technology and ignore the business side, because that for sure will be a failure. The market will not accept it if you have ignored the signals from the market that this is not a solution to any problem. As beautiful, as fascinating your technology is. And this is a big danger. I was there, and actually when I remember very well, I mean, how I built up and how I developed in Rockwell to be able to move away from that thing, and not totally away, it's to expand your thinking, to include more dimensions if you work. The technology is very important, you cannot abandon that. But you include other dimensions in your thinking. And lesson number 7 is that it is very difficult to develop a leading edge photonic product. It requires a lot of people. I talked to you about a team of 35 people for the diode lasers before. At Rockwell, actually, the systems group was 200 people. It requires a lot of people, it requires a lot of time. We managed to do it in a year, but mostly these things take many years. And as a rule of thumb, I can tell you, if you're studying for a PhD, you're going after the hero result. I managed to get one device that for a fraction of a second operated at a record, in a record way. And you're happy with that, and you should be happy. For the first time in the history of the world, you've been able to achieve something. But I can tell you that in general, the difficulty of getting there, the difficulty of demonstrating something for the first time is equal, and many times the difficulty of going from one to many, being able to produce in quantity and at a cost-effective price, is equal or larger, more difficult, larger problem than getting to one. And that's something that you learn very humbly as you fail many times in trying to make something that is cost-effective. And then come the startups. So those are the startups I worked for. Ortel was a leader in RF over fiber. Again, we were the first company, and I'm talking now 1990s, on cable TV, first company that developed fiber optic systems for cable TV applications. Then I was at Agility, which we developed monolithic widely tunable lasers for WDM, sensors, etc. Areas, we were into infrared imaging sensors, high power lasers, and miniature laser rangefinders. And this is a miniature rangefinder, for example. And in areas, we developed smallest and lightest weight rangefinders anywhere. They were designed to operate as an altimeter in small UAVs. And in Freedom Photonics, high power lasers, PICs, photonic integration for quantum sensing, and high power photodiodes. At Freedom Photonics, for example, we developed the highest power 1550 diode lasers anywhere, generating more than 10 watt out of one diode laser. And I'm highlighting these sort of unique things, best in the world and whatever, because that is something that you actually need in a successful startup. You need something that you're doing better, differently, uniquely, that differentiates you from the rest of the world. That will determine the success of the startup. And of the startups that I mentioned there that I worked in, actually, out of the 4 are in the Santa Barbara area. And this is no coincidence. There is a high concentration of photonics startups around Santa Barbara. It's actually just like Silicon Valley is called Silicon Valley. The Santa Barbara area is called the infrared corridor, like a Silicon Valley, but in this case, rather than silicon, it's because most of the companies there are involved with infrared photonics. And the corridor is because there is a highway that goes to their Highway 101. And for about 50 miles north of Santa Barbara and 50 miles south of Santa Barbara, there is a sequence of companies, mostly small, some that were small and became larger, that kind of spawned out of the activity in Santa Barbara. So in Santa Barbara, we have a very active photonic ecosystem. I would say one of perhaps the most active in the world. And the question then is why? Why did this happen? And there are many reasons, a large number of reasons. One important reason is that the University of California in Santa Barbara, starting again in the early 80s, purposely developed a strong presence in the photonics world. So new ideas come out of UCSB, which typically are associated with the PhD student kind of developing this idea. The PhD student finishes their PhD. And I don't know if any one of you have been to Santa Barbara or have seen pictures. It's very pretty. So a lot of people don't want to leave. And it's a little bit of the dilemma that Newton was saying earlier. Well, one way of staying is to become a professor at the university, but how many professors can there be? So the other option is to found the company. You start a company, and that has happened many times. It's one of the mechanisms. So there are new ideas that start in the university, and then the student that developed this doesn't want to leave Santa Barbara and forms a company, a startup. The university itself has mechanisms to transfer the technology. The intellectual property of the university is encouraged to go out. So there is an environment that stimulates this transfer out of the university. And obviously the university is a strong generator of trained personnel that then either form the company or join the company later, and that's key. In addition to the presence of the university, the National Science Foundation, NSF, about, I think 16, 17 or so years ago, had really an incredibly good idea to fund wafer fabs, nano fabrication facilities all over the United States. There are actually 12, I think, of which, I don't know why, but the dominant one, the largest, was set up in Santa Barbara at UCSB. So this was a wafer fab funded by the federal government, the National Science Foundation, to be managed by the university, but on condition that this would be open to industrial users as well, open to obviously faculty at the university, to students to be trained, and to anyone who would want to operate it. The facility was funded by NSF to get started with many tens of millions of dollars. It's hard, I don't know exactly what the total investment has been in the facility, but many tens of millions of dollars over these 15 years. And this can be accessed by industry at $142 the hour. So that is very cost effective. If it wasn't because of this, and these two things are key. It would just be impossible to start a company. You would need to invest then tens of millions of dollars in each one of the companies in terms of equipment, which is totally impractical. The fact that this facility is there has been the enabler for all these companies to be born. The funding of NSF, I think, I might be wrong by a few years, but I think it was set up such that it would go down over time, over 10 years, such that at the end of 10 years, it would disappear. And it did. And the facility did not disappear. The facility is self-supporting today. And it's self-support through this income, the $142 a hour that industry pays. Faculty using it, they also pay, but less than industry. And it's still there. It's managed really very well. It's maintained very well. And this is actually what I've used, our group has used in all of the startups that I've been involved with in Santa Barbara to process material. Another important element is funding. There has to be money, no question. Carlos also talked about that. This is the oil that drives industry. And there are many ways of funding a startup. For example, Ortel, where it was bootstrap funded in the initial years. That means that you're funding yourself through government grants, through commercial programs, through selling your product. In the case of Ortel, it was bootstrapped initially, as I say, but then received private investment after about 6 years, both from what's called angel investors. So these are private people that invest in startups. They're okay, they have no problem in taking the risk, and also received corporate investment. Actually, a Japanese company invested in Ortel, but none of them had control. We made sure that the control retained with Ortel. Agility Communications was venture capital funded, and venture capital in general means that you can get larger infusions of capital. They invest whatever is necessary for success. So it's much faster than bootstrapping. In bootstrapping, you're kind of trying to get the best of every day. But company control can be an issue. Venture capital firms would like to take control of the company. And then Aerios and Freedom both were bootstrapped all the way to acquisition. And there are pros and cons in all of this. Nothing is perfect, depends on what you want in life. They're all good and bad in their own term. Something that is worth highlighting in terms of funding is a program of the United States government that, again, I think has been a cornerstone. You need a university that provides ideas. You need a wafer fab where you can build your fabs, the infrastructure, and you need funding. And I think that society in general and government representing society has to invest in very high risk enterprises because the return to society is very high. And in the case of small businesses in the United States, there is a program called the SBIR program, Small Business Innovation and Research, where government agencies, by law, have to reserve a certain percentage of their R&D budget to be spent in small business. I don't remember exactly, I think it's about 4%. I don't know. I think it's 4. Yeah, anyway, if I'm wrong by only a few percent. Which 4% doesn't sound like much, but it's 4% of a very large budget. So it's actually hundreds of millions of dollars. So the Department of Defense, Energy, Health, Agriculture, NASA, and et cetera, each one of these agencies have an SBIR program and they all manage it separately. And you can access these programs as a small business. The mission, as I say, is the program is to stimulate technological innovation on the one hand and meet federal government needs. The federal government has needs. The Department of Defense has needs. The NASA has needs. So, say for example, at Freedom, we developed some lasers for methane sensing for NASA in the atmosphere. These are sensors that are either flown in an aircraft or in space, which measure methane in the atmosphere remotely optically. And they need a tunable laser. The tunable laser that NASA needed, they went down in an SBIR bid. We submitted a proposal, we won, and we built the tunable lasers that are used into this. So this is kind of how it works. The program is competitive, and if you happen to be selected, the program has 3 phases. There is a phase 1 that typically is between $50,000 and $250,000 for 6 months. And it's to establish the technical merit, feasibility, to see you spend 6 months, is it really worthwhile to continue, to carry this to the end? And if it is, then you go into phase 2, which typically is somewhere between $750,000 and $1.5 million for 2 years. And that is the R&D effort, which typically ends up with a prototype demonstration. And if that then looks worthwhile, it goes into a phase 3, which varies. It can be from a small amount of money, that's all you need to complete, to, in some cases, maybe tens of millions of dollars. And the SBIR program has been very successful, and many successes have come out of it. And one that I want to mention is, I'm not sure if you're familiar with the iRobot Roomba. It's basically a robot that kind of sweeps your house automatically. That came out of an SBIR program, for example, and many others. So lesson number 8 is, I mentioned earlier that you cannot develop a photonic product entirely by yourself. You need a team. Well, you need more than just an internal team. You need an external team. You need a whole environment, a whole society that is supporting you in that. You cannot do it alone as an individual. You cannot do it alone as a company, as a team, if there's nothing surrounding you. You need an ecosystem. And if you form a startup company, Gloria mentioned, you need a wafer fab, you need a university that provides idea and people, you need trained personnel, you need funding, government and or private. And those are the things we have mentioned, but actually there is even more. You need other kind of supports, accelerators, mentors, consultants, sales channels, very important. Remote fab facilities can work and operate as well. As saying, so that currently you can send wafers to process in Europe or in the United States or elsewhere. And that plays a role too. But that doesn't replace this, because in photonics, contrary to silicon integrated circuits, we are blessed and cursed by the fact that there is an infinite variety of material systems, an infinite variety of structures, of the types of devices. And at this point in the maturity of the industry, not everything can be done remotely. There are things that you need to do locally, and that's where the wafer fab plays. You need then also to have other startups, other business, and regulations that favor job mobility. In the case of the United States, for example, in many states, there are non-compete clauses. So obviously, if you work in a company, you cannot go to another company or form a company to violate the patents. I mean, obviously, that's illegal everywhere. But in many states, actually, you cannot even go and work to a competitive company after you've been working. So you've been working in a photonic company that, say, makes lasers for communications. You cannot go and work for a period of time, not forever, but for some time in another company that makes the lasers for communication. That is not true in California. California, you can move, job mobility is higher. And actually, I think it's not the only reason, but it is felt that why did Silicon Valley start in Silicon Valley and not anywhere else? And it's not the only reason, but this is one of the reasons. So as you know, in Silicon Valley, job mobility is dominant. People move like more often than you think. And that has nurtured, I mean, from one company, suddenly there were 3, there were 9, there were 27, and so on and so forth. So you also need a plan, and we're running out of time, so I'll go very quickly. But basically, you need to propose to whoever is going to fund you what you want to do. And any plan, any business plan, any proposal to the government, to a commercial, consists of basically 5 parts. You need to define what are the objectives, including the commercial ones, the payoff, what is the approach, what you're going to follow, what are the resources that you need, what is the schedule, and what are the risks. And if anyone is interested, we can put this in somewhere public, no problem. You can look at the details of what it means in each one of those later. But every proposal that you put together, one way or another, covers those 5 points. So in summary, in order to create a thriving photonic startup environment, which I believe from the little I've seen, which I'm not an expert whatsoever, but I think that you here are close. If not there, you're very close to being there. Maybe a few things need to be improved, and that is a key question. And one of the reasons why Natalia and me are here is to see how the IEEE Photonics Society can help you bridge those gaps, wherever the gaps are. Basically, society, mainly the government, meaning society, should provide technology infrastructure, mainly meaning a wafer fab, as I said earlier. Provide access to funding. Funding is key. Provide trained personnel, provide access to markets. And then what is it for you to do? Key is to come up with a novel idea that solves problems. Again, this is what I was saying. An interesting novel idea is not enough. It has to solve somebody's problem. And then articulate this idea in the form of a business plan, including the 5 elements that I mentioned before. And then work hard in all the details, connect with funders and customers. This is something that was also mentioned in the morning, fundamental. And then manage all aspects of the company, form a team, develop the company culture, set milestones, early prototype testing, and so on. And it's very hard work, but I can tell you that it is extremely rewarding. It will make you very happy. And with that, thank you very much.
Daniel, I think next time I'll go for the funding agencies pitching. I'm going to bring Daniel along.
Yeah.
Probably speaking on the behalf of the NanoFab facility we run here.
I'd be very happy.
Okay, so Felipe. We are a bit late on schedule, so I'd like you to be brief on your questions so we don't overdo it.
Thank you so much for this talk. I wanted to ask, from your several startup experiences, how different is it to do research in the environment from the FDA or
It is quite different. And I would say that the main difference is in academia, the desired output is knowledge. You're doing research because you want to increase worldwide knowledge, and that it is a very worthwhile cause. Knowing more, you never know where that will end up. So that is the main driver for academic research. The main driver for industrial research is to solve somebody's problem, where the technology is in service of solving that problem. So knowledge is important, but knowledge could have been gained somewhere else, and you adapt it in as much as is necessary to solve that particular problem. Is there another one there?
Hi. So I got happy when I realized that you also had a startup on radio wave fiber. Because I got a startup on radio wave fiber, and I'd like to ask your opinion about the future of the radio wave fiber applications. And also you mentioned high power photodetectors. How much power? you have in mind.
So they're connected, right? The high
Yeah.
power photodetectors were designed for RF over fiber. And those photodetectors can survive and operate well at about 100 milliwatt input power. And regarding the future of RF over fiber, forecasting is never easy, and I'm not very good at forecasting. I've been very wrong many times. But the big application for RF over fiber was cable TV, not anymore because now most TV is digital, so it kind of disappeared. But that was a big boom at the time, and at Ortel, we rode that boom. We were at the leading edge of implementing cable TV systems, and the company grew from about 20 or 30 people to 600 in about 2 years, driven by cable TV. But today, unfortunately, I don't see any application like cable TV. The main applications today are in remote antenna for defense purposes and some for commercial applications as well. And the market is very small. So there is a need, but not a big market.
Thank you.
Okay, with that, I'd like to thank Daniel again for this talk and follow on.
Yes. I knew it was something with the 3 or 4. Thank you.
Okay, so we're gonna follow on with Dr. Kyle Spapson. Kyle is a physicist, U.S. Navy physicist working and then directing the Office of Naval Research Global in São Paulo. And he has a physics background, got his PhD in Maryland, University of Maryland, and working on gyrokinetic methods for computational field plasma physics. And after his doctoral work, he started working on National Science Foundation, got a very prestigious award there on rhythm. A bit off your background, right?
Yeah.
Rhythm, mammalian cellular genomics, and he would work on Switzerland on that. So he has extensive research background on multidisciplinary topics, several papers on important journals, and we are eager to hear your comments on funding. Thank you, Ray.
Yes, thanks, Gustavo. It's a pleasure to be here. Thanks to Daniel for the invitation to join this session and take some of his time, I think. I live down in Sao Paulo. I've been up to your future Campinas pretty recently with Tiago, seeing the labs next door. But this is a really interesting opportunity. I'd like to help make the connection between basic research, which is really my main goal, to fund basic research. And I'll talk about that. But also connect that with what you're talking about here in this workshop, which is the entrepreneurship, because the Department of Defense, whether it's the Army DEVCOM down here, or the Office of Naval Research Global, which was first in Sao Paulo and has been followed by the Air Force and the Army research offices. We always want to have uses in mind. So we fund basic research because we think 20 years from now we don't know what the most important technology will be for national security and for global security for our allies. So we fund basic research, but we want to have something in mind that it might be useful for. And it's really great to connect these two communities, entrepreneurship and basic research. Gustavo was nice to give my background. I have moved from physics to biology and then back into machine learning and applied mathematics when I started working for the Navy. And now right now I'm on a 3-year tour with the Office of Naval Research Global. ONR Global has offices in Santiago for 20 years, in Chile. We have Sao Paulo for almost 10 years. The office in London was founded right after World War II, Tokyo in the 70s, Singapore and Prague in the 80s, I suppose, and Melbourne is actually our newest office down in Australia. So we go through these rotations, and our mission down here in Sao Paulo and around the world goes back to this law from 1946 that stated that the Navy needs to engage in worldwide scientific information creation and coordination and making it available to the Department of the Navy. So a long tradition of basic research funding in the Navy. And one of our, best outcomes, and we could stop here and say that entrepreneurship is a different thing, but I think we should point out that many of these Nobel Prizes awarded, from lasers to to quantum systems, nonlinear optics, all these Nobel Prizes, which were partially funded by the Office of Naval Research, they all have great applications, and we all know the technologies that have been very profitable that have come out of these Nobel Prizes. And so, not every Nobel Prize leads to huge profitable industry, but many of them do. And so I think the connection between excellent high-risk research and successful businesses is pretty obvious from the history of great people winning Nobel Prizes and the DoD funding them. So my goal here is with the International Science Program is to fund basic research. We have research grants, we have visiting scientist program, we have conference funding, and all of those are focused on the low end of the tech readiness level scale. So basic principles, a concept, maybe a proof of concept of a critical function in the first experiment. And these might be the hero type of studies that someone just mentioned. Daniel mentioned going from 0 to 1 is what we're trying to fund, and we're trying to de-risk that deep tech, those technical challenges that can make it difficult to go to market. And so, if you already are thinking about a business or a small business, a startup someday, but you're still in the lab, maybe you're the professor or the student, and already being very ambitious, ONR Global is here to de-risk at these very low levels of tech readiness. And so we can fund the university research, but we can also fund research in a small business. It doesn't have to only be a university. We can give a grant to an entity that's registered in our system, and as long as we deem that research to be low TRL, so de-risking the technology, we can fund that. And we really like to find these examples where the technology application is closer than in some other cases. And I think that brings me to this point where there's a consideration to use the technology, and then there's the university quest for fundamental understanding. And some people are tinkering around the lab, which just means poking on the dials and seeing what happens. Some people are really interested in the pure basic research. That's the TRL1. Sometimes we call that 6.1 research, but the low TRL level. And then there's the applied research, invent the light bulb and experiment with the engineering. We don't fund that out of my office, but I think what the sweet spot for us in the Office of Naval Research Global, at least, is to find, research that is fundamental to understanding physics or understanding chemistry, understanding photonics, let's say, but has a use-inspired component to it. So it's not just, pure research is great, and we do fund pure research, but finding something where you have an idea of where it might be in 10 years, and that there needs to be something discovered in your lab now, that's what would be the best project for us to fund. And so the scale of the money from this slide looks very big. The U.S. academic research and development expenditures is $50 billion inside the U.S. We don't take that much money outside the U.S. And in fact, I'll come back to how much we spend outside the U.S. It goes, we have a very great point to invest in Brazil and South America. We have great return. Someone mentioned that the people here in South America are just as qualified, very well trained as people in Europe and the U.S. But finding them and getting them funding and connecting them to the ecosystem is part of the exciting thing that I get to do down here. So the DoD is a slice of the academic research expenditure. It's only 15%, but we turn out to be the top funder in both computer science and engineering. So that's where our focus is: physics, math, engineering, computer science. That's where DoD research at the academic level is focused. And this slide shows just the DoD. So now this is just the DoD S&T budget is $20 billion. Half of that is going into a higher TRL level, advanced tech development. What do we actually need to put onto an airplane or an aircraft carrier? Some of that is applied research that goes on in some of our applied research centers. So a third of that is applied research, but still The rest is 6.1 or TRL 123 basic research, which turns out to be about $3 billion. And then the Navy, the Army, and DARPA, which was mentioned earlier in Natalia's talk as being a customer for products. We split it somewhat evenly between these agencies. So the way, and so I was going to say, how much of that is spent overseas? The Office of Naval Research Global, so Navy, takes about $20 million per year and spends it overseas. So I manage about 10 grants, and in Brazil, they're about $100,000 per year. In Europe, we have 10 people like me going around. In Japan, we have 3 or 4 going around Asia. We each manage about, say, $1 million a year in grants. So they're pretty small, but they're meant to be seed funding. And like I pointed out, I guess on this slide and the others, and as Daniel pointed out, with small business investments, going from that seed funding to something much larger and more interesting and more profitable is something we'd like to help you do. And I'll come back to that at the end. That was what I wanted to mention, perhaps for this audience most. But I do want to give you my standard pitch on what we fund. So we have really 3 different programs plus a bonus that we use to distribute this funding to our collaborators and friends in the rest of the world. First, the Visiting Scientist Program. So this is to pay directly to a person for a travel to a conference and to visit a professor who is funded by the Office of Naval Research. So if you look at research papers that come out of the US, you'll find ONR or AFOSR, so that's Air Force, mentioned in the acknowledgements of half the papers in the country. And so it's easy to find a scientist who's been funded by the Office of Naval Research, and you could go visit them, and that would help you pay for that trip. The second thing we do, which is a bit larger, is the Collaborative Science Program. I think of this as conference funding, conferences and workshops. So, for example, next year at this workshop, we had a research day to present the latest results from the research side. As a complement to the entrepreneurship side, I could fund part of this conference. That'd be great. The largest thing we do are the international research grants. And these are the ones, say, $100,000 per year for 3 years, which are seed funding to de-risk your deep tech ideas and get to one of those exciting papers that we know is really the goal of the university researcher at the base. The bonus here, the Global X Challenge, these come up once per year, and we have specific topics. We can talk more about that some other time. I'm going to skip this slide, the details, running short on time. We can talk about that later. How to get a grant. This is the list of grants that we currently or recently had in Brazil. I guess I'll just mention this one. This is nice. This is Professor Daniel Felinto up in Recife, doing quantum internet based on atomic ensembles. So that's a 3-year grant for about $100,000 per year. I'm trying to get more in the area of quantum information and photonics as well. I think this is a good audience for the intellectual property slide. We're not trying to buy any of your intellectual property, buy your IP. These are research grants. The only caveat to that is if you publish a paper with the research that we funded, then a scientist at a government lab can read that paper and develop a product based on what you published and not have to pay you royalties at some point in the future. That's what we call government use. And it's really, there's no profit that the government's going to make off of that, but if there's open literature and you've published it, I think it's often understood that could be used for further development. But we're not buying IP, we put no restrictions on how you use what you discover. So we're funding research grants with our basic research funding. The Global X Challenge I just mentioned, this closed for the year. This slide was from earlier this year, so the cycle ended in September this year. So we'll have another one open in April. So it's time to start maybe thinking about what you need to do to put a proposal together. But we haven't announced the topics yet. So this past year, the topics were long-range underwater communications, which I think Daniel helped with. We have the 2D woven fibers for multifunctional fabric. It's like clothes that are smart and protective, or maybe generate energy. And I guess that gets into personal expeditionary power. So like batteries in your shoes that capture energy. So some really interesting topics that are much more applied. So higher TRL and maybe much closer to something you could sell it could be dual use. You might sell it to the DoD in the US, you might sell it to the Ministry of Defense in Brazil, but you might also have people who want power producing shoes who are not soldiers either. So this can be really interesting. And if you're interested in that, send me a message and I should make a list and send you an announcement that opens next year. Okay, I think here's the exciting thing I don't usually talk about that I was excited to talk about with the entrepreneurs is the very early stages of a concept that we call Titans. And I put the acronym on the next slide, but it's not a big deal. This is the sort of the Titans pipeline that we'd like to develop. And I'll say we have no examples of this working yet. And this is an approach that we're trying to use to bring together the entrepreneurship, small business innovation, and the actual profit on the one side with the basic research, which is really the core of what we do as in Office Sustainable Research Global. But we have access to all of that other funding, that small business funding, which Daniel said 4%, it's 3.2%, and it's all, but you can add 0.45% on a technology transfer, so rounded up to 4. So we got about 4% of that going to small businesses, but then just, the purchasing. Like if the DoD decides it wants to buy your battery technology, they might buy 1 million units. And, so there's very large scales here. And so having access to a DoD market in the US could be a really great thing. Like I said, no, we don't have any examples of this working out yet, but we're trying to find ways to bring your use-inspired basic research ideas into a potential market fit, probably in the US somewhere, but potentially globally as well. So, we fund your technology, your disruptive technology, and de-risk it. We take you to a government venture partner who might be a small business, SBIR company. It might be one of our internal, like Defense Innovation Unit. We have these internal venture partners inside the government, and then help you get to the private venture capital. So that's a long road, and I don't personally know how to do it. This is a concept we're putting together. So if you have a proposal for a basic research project that I'm going to evaluate, it would be nice if you have an idea for entrepreneurship to talk about this as early as possible. Restating what I just said with the acronym that probably should have been on the previous slide, towards investment for technology acceleration into naval systems. And so, I'm from the Navy, so these are naval systems, but I think dual use technology that's outside the DoD, but also technology that could benefit the Air Force or the Army as well, is included in this umbrella. Just another pitch slide for that idea, but I think I want to finish up. So myself and Arturo, we work for ONR Global in Sao Paulo. Arturo has spent most of the last year and a half traveling throughout Mexico and finding opportunities there. Dr. Colonel Roger Greenwood is the Air Force Director in Sao Paulo, and his colleague, Dr. Light, is a microelectronics expert who worked with the Air Force for a number of years. And the Army, the International Technology Center from the Army DEFCON, just hired a local scientist, Pilar Viana. She's getting up to speed, but she's a PhD chemist, and she's going to be a really important part of our team going forward. So that's my email address, and I'll give you my phone number if we chat afterwards. We're basically looking for proposals, but on the slide where I described how our proposal process works, maybe I should go back there since I'm saying send us your proposals. The point of this slide was to say, we make initial contact, send me a white paper, by which I mean just an idea of a project. No budget, no deep dive, but just like, do you have something that might be interesting? And then we can have an informal conversation about whether that sounds like it will be a good proposal. And then I would ask you for a full proposal, which has all the budget details, and go through the grants.gov website, conduct the research, and publish the results. That's the whole grant funding cycle. Again, we're not buying any IP or restricting you from anything. We are looking for the most high risk, high return type of ideas where you don't know if it's going to work out. You don't know if there will be a business or even a market fit someday, but we'd like to help you get closer to that determination with our basic research funding. I'll go back to my my email address so you can stay in touch. But I'm down in Sao Paulo. It's an easy 90-minute drive. I'm always happy to come to Campinas. So, but thanks for the time and for the invitation.
Thanks, Kyle. Any questions? Low battery.
Lunch is approaching. I know we got one more time.
Any questions?
I have a question. You mentioned it as long as the circuit's public, and we use that. I understand it's actually not as obvious, but that's kind of like the year research. The university or the researcher decided to file for a patent. How does that go in terms of that?
So we have no role in intellectual property registration, right? So we might be able to help you. The Naval Research Lab might be able to help you with the U.S. patent process if we're really excited about what you're doing and you want us to help you. But we have no terms where we interfere with your patent application. If you wanted to have help in the U.S., we might be able to find a collaborator to help. I think that there's a larger point there about if we fund a basic research grant in your lab and you have a collaborator in the US as early as possible who might be interested in working with you, that's always a great scenario. So it could be a collaborator at the Naval Research Lab or one of the applied physics labs, for example, but it could be a university collaborator. And then probably if you get to something that you want to patent, there would be a cross-border collaboration on the international patent. But and the easy answer is we don't interfere with your IP and your patents at all. We'd be happy if you patented your idea and turned it into a product. That's the Titans concept, is that we want to help you bring it to market in the US.
Okay.
Yeah.
Thank you for the talk. Just one question. So those DoD also funds facilities or only personnel, only like researchers?
So each of these basic research grants goes to an entity, say Photonics, and they would manage the money. They would go to a research lab, and whoever the PI is on the project, they would spend the money on their personnel, their consumables, small equipment. Could buy, sometimes lasers are $100,000, that's too much. But if the equipment is less than a third of the cost of the entire grant, maybe less than half, if it's really important, we can fund that. But yeah, facilities are a pretty hard no for my program. There are potentially other programs, like the National Science Foundation builds antennas to monitor space weather in down in Patagonia and down in southern Argentina. So, there are very specific facilities, but my program can't do facilities. If you have an idea for something, I can try to get you in touch with someone. Yeah, Daniel mentioned the wafer fabrication facilities in the U.S. I don't think we have a mechanism to build those overseas. Would probably be a good idea, though. Yeah.
Further questions? Okay, in the interest of time, let's move on to our final project. Thanks, Kyle, again for it.
Thank you, Gustavo.
You're welcome. I'm gonna ask for help here. I don't know how to get the next speaker on the screen.
Yeah.
Okay. And I'll do what CB also asked for, which is get the audience on the screen rather than just not too much. There you go. Okay, so our next speaker is Paulo Danese, Dr. Paulo Danese. He's might be known to many of you. He was did his PhD, got his PhD degree from the Physics Institute here at Campinas in 2006. He then moved on to Corning Incorporated in Corning, New York. He stayed there, I think, up to 2012. And he came back and started a professor position here at Unicamp and stayed here till 2018, if I'm not wrong, and moved back to Corning. So it's a great pleasure to have him over. Paulo.
All right, can you all hear me okay?
Yes.
Okay, good. Thanks, Gustavo. Yes, that's right. I came back to Corning in 2018, and I'll talk a little bit about what's going on there. So let me first get my slides right. Do you see the full slide or you see the presenter's view? Hello?
Just a PowerPoint screen. So.
It was a full slide.
Yeah, there you go.
Do you see the full slide or you see the presenter?
Full slide.
Okay, great. So, yeah, thanks for the invitation to participate in this workshop. Unfortunately, I couldn't be there in person. Maybe next time. So, as Gustavo said, I am a scientist at Corning, and I'm also a research director for exploratory projects in optical physics. So when I was talking to Newton and Gustavo and others about the workshop and motivation and the context, everything, one of the motivations was to give students an idea of potential path or career path besides academia. And so there are lots of talks about startups, how to fund your own company, etc. And obviously another path is to do research in an industrial lab. And so what I decided to do was to put together a few slides that talk about Corning research. And hopefully that's going to illustrate what is it like to work in a company, in an industrial laboratory, what kinds of research, how do you fund research, what are the areas that we are interested, so on. So that's sort of the context to my talk. So it's an introduction to Corning science and technology, again, with the goal of perhaps illustrating how it's like to work in an industrial laboratory. So before that, there is a short video here. So you guys excuse me, marketing video. I didn't make this. Just introducing very briefly Corning. So hopefully the audio is gonna work. So let me try.
Where's Corning? Some may say a town in upstate New York. Population 10,709. And they wouldn't be wrong. But that's not the only place Corning is. Because Corning is a company that changes entire industries with its technology by partnering to create innovation that will turn the heads of sci-fi writers. When you ask where is Corning, it's here, 4,200 miles away, at the bottom of the Atlantic, part of hundreds of millions of miles of fiber optic, connecting countries, continents, and billions of people around the world. It's also here, in that super tough yet sensitive interface between you and your phone. It's here, 340 miles above the Earth's surface, in the Hubble telescope, in its optics, and here, in the glass on the International Space Station. It's here, in the screens we view every day, producing unsurpassed clarity in every size, from the colossal to the compact. It's here, in the ceramic filters that make the air we breathe cleaner. But Corning is only part of the equation, because our spirit and drive can be scaled at speed when we partner with customers who want problems solved, turning hypotheticals into innovations. Here, here, and here. Oh, and here, and here, and here. Corning, we put ourselves into everything.
Okay, so yeah, like I said, it's a marketing video, but I always find that it's better with it than without it. At least it gives a little bit of an idea then of what the company does by showing images and so on. So anyway, so the company was founded in late 1800s. It's been around for about 170 years. It's located here in Corning, New York. This is where I'm at now. There's 65,000 employees. It's a company with medium size, about $14 billion in sales. Out of that, we invest in research and development about $1 billion a year. That is, so I want to make a few comments on this slide that are related to the impact to research. So first of all, a company that is that old, how does that impact our lives as a research inside the industrial lab? And one of the obvious ways is that the company has a long-term view on its future. It has survived for all this time by creating capabilities that will be useful for a long, long time. And when a company has a long-term view, that favors investment in research. And so as a scientist, when you're proposing an idea, you're proposing to work on a subject in that, with that view, things become much more, easier to make your case. The second thing is that throughout this time, the company went through many ups and downs. There are many, many examples in its history where innovation helped the company come back from a bad position or a low market, etc. And so that builds a culture that investing in certain areas, investing in RD&E, will have an impact in the future and will help the company through difficult times, in addition to, of course, creating products for when the times are good as well. And so it's not just the scale of the investment, a single company investing every year about $1 billion in research. It's also the aspects of this long-term view that helps quite a bit. The company has multiple businesses. I won't dive into this. I just want to show some of these areas because as a materials company, and this is a conference or workshop about optics and physics, and that's my background, you want to make a connection how optics and physics is relevant for all of this, and it's basically everywhere. I mean, so there are businesses in displays, consumer electronics, optical communications, maybe the most obvious ones, automotive, life sciences. There are a number of others that are not here, aerospace and defense, for example, and micro optics and many others. But in every business, I know of projects and people that are working with very deep background in optics and optical physics, and there are opportunities for a lot of them. So that diversity of application spaces or areas that the company has also is an incentive for the researchers that can find opportunity in those areas to propose projects. The other aspect is that the company, it's a materials company, so we make a lot of things, and it's illustrated by these numbers. There are 122 factories around the world on all these businesses that I mentioned. And specifically, there are 10 research and development centers. Some of those are illustrated here. So we do have a research center in Sunnyvale in California. There's one in Montreal that is mostly on software. There is a group in France. There's another group which used to be in St. Petersburg. It's now in Helsinki, which is a group on modeling and simulations. And there are a number of other labs in Asia and China, Korea, India, and so on. These labs, they are connected. Obviously, I work with people that are in Helsinki, or people that are in the Sunnyvale, in my project teams, and so on. But those are smaller labs. Corning has a model that we do have a centralized laboratory in Corning, New York. That's where most of the projects are. And then the satellite labs are connected to them. So this is the lab in Corning, New York. This is this is a Sullivan Park Research Center. This is a building that has about 2 million square feet of area. There is no office, there's no commercial activity or business or anything. This is entirely dedicated to research and development. There are about 2,500 people working in this lab with 500 PhDs and so on. And I want to spend a little bit of time here talking about some aspects that I think are interesting for students to know or to visualize. Oh, by the way, I'm right now located on the last office right here. So I do have a nice view looking at the windows. Many times I see deers and bears and so on, but luckily there's a fence so the bears don't come close. My lab is somewhere here in this building. So I actually walk quite a bit every day to the lab and back. There is a cafeteria, let me see, right here, looking out the window as well. And so some of the things that I want to say being in this environment. First, there is a big sense of a community. And I think Daniel mentioned something like working on a team and being part of a group. This is really strong in this building. All this community, like the 2,500 people, are everybody working on research and development, and you are constantly in contact with other scientists. In the cafeteria, there's a famous table, there's optical physics table, so I go there almost every day, have lunch with a bunch of other folks that are working on projects and talking about what they're doing and the challenge they are facing and what they've learned and things that you do, with talking with colleagues that work in similar and different fields at yours. So that being able to live in an environment like this offers you that opportunity that you can interact with a lot of people that are doing research on a daily basis and product development on a daily basis, and that's very nice. All the labs are in the same facility. So as I walk to my lab, I ran by a bunch of other labs that I'm free to go in and talk to people, see what they're doing, go to their offices, have individual, one-on-ones with people that are working in all kinds of fields. That's another advantage of being centralized like this. The other thing is that you have access to a lot of capabilities. For example, in this building right here is our clean room, where we have a lot of tools for nanofabrication and people that understand, etc. We have a department that is called Characterization Sciences, where there are all kinds of techniques, all the way from microscopy, Raman spectroscopy, so on. Fabrication, right, as fiber fabrication and components and so on. And so it gives you access to a lot of capabilities. So there's sense of community that you talk to people all the time, access to capabilities and so on. The other part that I want to highlight is that the management or the research and engineering management, they are also in this building. And so the head of research sits in this building, the head of engineering sits in this building, the chief technology officer sits in this building. So it's not uncommon that the CTO of the company is walking the corridor and he's going to stop by your lab, or the head of research. And so it provides that environment of discussion right to the top on the topics that you have going on in the labs. We also have our own clusters for scientific computing. So that's another capability. Let me see what else I want to highlight in this. There's also another point which I think is really interesting and is a consequence of this environment, which is how the ideas are funded. You would think that this is maybe a top-down approach where the leadership is going to tell, how, in which project you should work on, but it's actually very much different than that. It's a very diverse process. Of course, you have cases where the whole company is interested and you need to put an army working in a certain direction, but there are many opportunities to fund seed projects, smaller ideas that come from the community up towards the leadership. And that being in the same building with everybody also helps these types of discussions and engagement. So those are some of the comments that I wanted to make right up front as you look at this beautiful building, and it gives you a sense of the things that we experience here. So as I said, there is $1 billion every year. That's about 7 or 8% of sales, not profit, which is a very large number. 80% of that is aligned with businesses. What does that mean? It means that take a division like telecommunications, and they have a roadmap of 5 to 10 years of what's going to become important. And so related to that, you can propose projects and work on problems that are going to be relevant for that. And 20% is allocated to what's called exploratory, where it's just simply not connected to any existing business of what Corning does. And that's a very, very large number, considering that 100% of funding is the company's own money. So the company is organized by, the research community is organized by core capabilities. And so when you look at these boxes, you see things like thin films and surfaces, materials and process characterization, applied optical physics, so on. And these competencies, they may represent one group or multiple groups that are in that area. And so I am part of this group at the moment. I work a lot with people, thin films and surfaces, modeling, of course, characterization sciences, communications as well. And there may be multiple groups within a certain competency. And so as a scientist, you will be in one of these groups, and most likely the projects that you work on will involve people from all the other groups. And so I think Daniel mentioned that as well, right? You will work with multidisciplinary as a team, and so that's very much the case. And I think maybe the uniqueness of this is that in Corning, all of these teams are in the same place. And the other part that I want to mention is you also have teams much later in the development. So teams that are doing product development in the same team. And so it was mentioned before, right? You're doing research, but you have to think about all the way which problems you're solving, how do you scale your whatever idea that you have, and so on. And so being able to interface with the product teams, people doing the engineering, the product development, is also a significant advantage in my view. It gives you early on the right questions to answer, and so on. There are a number of examples in Corning's history of products that were created through this environment. As a lab, even though the company is 170 years old, but as a lab, Corning has over 100 years of R&D. And I'm not going to discuss any of these, in much details, but this is what I mentioned before, that having such a history of successes and things that brought the company back from really difficult times, it really creates a culture that values the research and supports the research. So of course, perhaps the light bulb was a famous one, working with Thomas Edison. This is kind of a little bit of a history. This is the order from Thomas Edison to develop the vacuum bulb for his lights. And then Corning, after that, developed something that was called the ribbon machine. I hope you can see the video, but it's this automated process to make these light bulbs. And why I'm saying that? I'm saying that because many times the research that Corning does, it's not just about the material or the thing that you're trying to make itself, but it's also about the process. How do you make them at scale and so on? And taking, like Daniel said, taking one from the lab to a factory where you're making many of them, it's not just about automation, and it's about understanding every failure mechanism that is involved on that. And so you really have to understand not just why that one experiment worked, the one hero case worked, but what are the possible mechanisms that could make it fail. And of course, this is a very early example that really boosted that culture in the company, and it's still around. Corning, broadly speaking, Corning's approach to innovation involves creating very deep capabilities in certain materials and processes, many kinds of glass and ceramics and engineered materials. Obviously, the company is looking at applying this expertise to solving problems that create value to customers and are high value, that you can fund back all of this. It's always a partnership with customers in various areas. And in the end, the model for Corning is to develop this particular components that they call keystone components, right? Could be the optical fiber itself. It can be a surface of a glass that is engineered for a certain property, and so on. And so this overall model opens a lot of opportunities for research. Those opportunities can be in actually developing this capability. And so you may propose as a scientist, I want to learn how to model electromagnetic surfaces, a very large scale electromagnetic. So a problem that is open in the literature at the moment is going to be important for Corning in the future. That's an example of a capability. Of course, you can work on understanding applications. And so, for example, we have teams that study transmission in optical transmission, even though we don't sell systems. So this framework opens up opportunities for all kinds of projects. And so in that, we always, people always ask, right, is Corning funding long-term or short-term research? Is the research applied or is it fundamental? Is it are we mostly solving problems that the customers bring, or are we also doing a kind of technology push that develop internally on? And the difficulty that I always have in answering this is that when I actually look at the projects and how we are doing things, drawing that line becomes actually very difficult. I see many projects that, yeah, they do have a short-term goal and a short-term delivery, but when you start looking deep enough, they open up questions that are going to take a long term to answer, and things end up driving towards that. Are we doing more applied or fundamental? I don't know. I think some projects are very applied, yet there are certain gaps that we do have to generate the fundamental understanding internally ourselves, and so on. And so that's a long discussion. I'm not going to get too much into it. I just want to mention this, that you take pure basic research where the goal is sort of improve understanding, and then maybe you define applied research as pushing a technology from what it is to improve, and then the use inspired that I think Kyle mentioned as well. This is just another way of kind of framing it, but the way we see it, yes, of course we're looking at use inspired, of course we're trying to create products, but all of this is connected. And in the research environment, existing understanding create potential use as well as existing technology. But when you start looking at the problems, they also open opportunities for improved understanding and improved technology. And so in that environment, our projects are very diverse. You have things that are, no kidding, targeting, solving a customer problem, developing a product, as well as things that are super early on in understanding certain physical mechanisms, for example. So anyway, I'm going to show now 2 examples of projects in optics and photonics that hopefully illustrate some of the things that I'm talking about. First one is this. There's a little video. Okay, so of course the goal here is not to discuss the specific projects in detail, but this is an area of an optical backplane, or for co-packaging optics and other names, but it involves creating this glass substrate with waveguides, coupling to photonic chips, electrical lines through glass via singulations, laser processing of interfaces, and so on. And all of these are areas that Corning is working on. So examples of laser singulations, optical waveguides through glass vias, so on, are all areas that we have research going on. And so a case like this, it's not hard to imagine that, yes, there's a clear connection to potential use cases and interaction with customers and products that are going to come out of this, but there are also a very large number of opportunities for more basic research, and all of this happens. Another example, this is just some images of prototypes, and so is an area that I'm working on as well, creating meta surfaces. I won't get into too much details, but this is about patterning the surface of the glass to create certain functionalities. So we study the physics of these surfaces, fabrication, and creating devices out of them. What are the motivations for this? This is a potential platform to create functionalities on an incoming field, so manipulate an incoming field on a common platform. You configure the patterns to behave as a lens, as a beam deflector, as a polarization splitting, and so on. And not to rush too much, but this is a very broad area. One example that we looked at is perhaps the future of micro-optical components. Many of you are familiar that this is a product, an example of a micro-optics product, that each function is created by an individual component, and that component is fabricated by its own process. And so from a scalability point of view, this is something very difficult for optics. It's what maybe Daniel defined as a blast in a curve, right? Because yes, you can do a lot of things, but it also requires you to handle many different processes and then assemble all of this. And so the more you can consolidate, and in this particular case, I won't get into much details, but this entire function was implemented on a single surface like the one, and you can see how compact it is and so on. So it's an example of a project that, yeah, you can see how this can be connected to a benefit in large scale manufacturability, but it requires a lot of physics and understanding, and that's what we are working on. So to conclude, hopefully this overview of Corning Labs give you a little bit of an idea of how is the life kind of work in an environment like that. We do have these core capabilities that we develop. We have a centralized research lab and everything that comes associated with that. There is a continuous investment given the long-term view of the company, the history of successes in the past. There is a broad spectrum of projects, early stage, later stage, fundamental, applying, however you want to define it. I think you can find opportunities here. The diverse set of businesses also open a lot of opportunities for optics, because optics is critical in many of those areas. There are many funding mechanisms, and I guess another the part of this is that in this environment, as I mentioned, there's a lot of opportunities for you to propose the kinds of things that you want to work on and make your pitch. So with that, I am open to questions if there are any.
It's a second we're figuring out the audio here. Okay.
I'm sorry?
Yeah, we're just fixing the audio configuration here. So we can take some questions. Gonna shoot first. Before let me start off.
Okay.
Are you the one?
Well, no, you can ask.
Paulo, is there a possibility that, let's say, if we start working on something that may become a spin-off from Corning, is that a possibility? You think?
So Corning has a group that sort of fosters creation of new business within the company. And so it's a whole group that has a structure with people that think about the product and the business and interact with customers and so on, and interact with all the research groups to pull some of this and potentially create a startup like inside the company. So this is common. It does happen quite often. There are many initiatives that end up being like that. So in other words, the result of the work doesn't necessarily go to an existing business, but it may create a new business unit. So I would say it's more of an internal startup type of effort, not so much externally, meaning become a separate company from Corning.
Thanks.
Your question? Okay, follow on mine. So follow.
I lost your audio, Gustavo.
Can you hear me?
I can hear you now. Yeah.
Okay, so I was asking how does Corning approaches startups when you are looking for new technologies and something like in the culture of the company of looking for the market and figuring out whether there are technologies out there being developed at startups that could be either acquired by Corning or partnered up with Corning in the technology development process. Can you comment on that?
Yes, absolutely. That same group that I talked about, their role is not only internal but also external. So they are all the time interacting with startups and bringing startups in and having discussions about synergies and so on. And yes, Corning does make investments in a number of startups.
Anyone else?
I follow. Just follow up also on the same question. Is there any case of startups outside the US?
Yes. It's not restricted to the US. This one of the reasons why we have these satellite labs is in fact to be close to places where you have a lot of activities in technology, and these labs are constantly looking at opportunities as well. So it's definitely not restricted to the US.
Okay, if there are no further questions, I'd like to thank Paulo again for this talk.
Thank you.
Okay, thank you, Paulo. Thanks a lot for joining us. We meet soon at some other opportunity.
All right. Thanks, guys. Bye-bye.
Thank you, so. Quick announcement. And I'll do that in Portuguese and English. Actually, first thing. The Tor Labs AFN is not working. And it'll be working till 3 p.m. Every time we're gonna. So if you want to see it, till 3 p.m. Number one. Second, we gave you the keyword, and the keyword was optoelectronic. So, but because we have to be back at 1:30, so we're gonna be doing the selection of who's gonna get the prices at 1:30. So when you come back at 1:30 sharp, we're gonna do this from 1:30 to 1:35 and only be 5 minutes late for the afternoon session because we are running like half an hour late. Okay, so I hope to see everyone here at 1:30. Now in Portuguese. Então, a gente está sorteando o AirPods, mas a palavra-chave é a optoeletrônica. Vai ter outra depois para tarde, para a gente dar no final do dia. Então, só que a gente está muito tarde, a gente vai fazer agora, só que a gente só tem 1 hora para ir e voltar para o almoço. E como está todo mundo muito faminto, tem que comer alguma coisa para a gente voltar às 1h30. À 1h30 a gente vai fazer o sorteio, mais 5 minutos. Se 1h35, se você ganhou, vai para o próximo. Tá bom? Entendeu? Vocês ganharam e aí, nessa primeira, que as pessoas não aprenderam ainda mesmo, que ela não falar, então estou falando a palavra-chave, optoeletrônico. Então decora. Aí eu te perguntar qual que é a palavra, você tem que falar optoeletrônico. Tá bom? São 5 coisinhas, lembranças. Um é um AirPod, acho que é chique. Tá bom? 1h30, todo mundo de volta. E o AFM da Tor Labs vai ficar funcionando. Ele estava com algum problema, mas está funcionando. Quem quer ver funcionando? Até 3 da tarde. Eles não vão estar para o outro coffee break. Tá bom? Então, eu espero todos até 1h30. Exato, não é 1h35, é 1h30. Tá bom? Obrigado. Obrigado, Obrigado.